Let me start with an example in this lecture. So we are given two random variables x and y. Okay, they are jointly continuous. And their distribution is pretty simple. It is given here. They are uniform on the unit square. This is a unit square. So they are a uniform random variable on the unit square. In particular, each one of the random variables is uniform on the unit interval. So the interval is unit. When I say unit interval, the length is 1. And the two random variables are independent. Another assumption is independency. Independent. X and y are independent. Now what we want to find is the distribution of the ratio of the two random variables. So we need to find out the ratio of the two random variables. Let us say y by x. So this ratio, let me call g of x comma y. Why did I put x comma y? Because it has two random variables, function of two random variables. Okay, so I wrote g of x comma y. Let me call the g of x comma y function by a random variable z, capital Z. Now how do we go about it? How can I find it? Well, the same procedure, that is cookbook procedure, okay, that we used last time in the last lecture for the case of single random variable. If you have single random variable, there we did it. So like y equal to g of x. There also we used this cookbook procedure. What is a cookbook procedure? First find the CDF of the random variable of interest, that is y, and then take the derivative. That's all. This is the two-step procedure. Okay, the same approach that we are going to use here also. Okay, so the cookbook procedure that we used for this case also applies to the case of where you have a function of multiple random variables. This is a single random variable. Same cookbook procedure, we can use it for multiple random variables. Procedure is same. Okay, now we know the cookbook procedure, and then the first step is find the cumulative distribution function of the random variable of interest, and then take the derivative in order to find the density. That's it. Once you take the derivative of CDF, then you get density. Okay, density of the random variable of interest. So let's find the cumulative distribution function. By definition, the cumulative is the probability that the random variable is less than or equal to the argument of the cumulative. So the cumulative distribution function is denoted by like this. So this is the argument, and this argument is less than or equal to the random variable p of z less than or equal to a certain number. That certain number is the argument of the cumulative. And we know what is z equal to y over x. So this I can write p of y over x less than or equal to I'm sorry, this is not y, this is going to be, let's say, z, because the same argument comes here. I wrote wrongly, I'm sorry. So this is going to be z. This is a definition. Okay, now if we write this event in terms of the random variable of interest. Okay, so this is a probability. Which one? This is the probability of the random variable of interest. This is a probability that a random variable is less than or equal to small z. So now what is this? The ratio is going to be less than or equal to small z, if and only if the pair like x comma y, the x comma y happens to fall below the line that has a slope z. See, I have the uniform random variable like this. This is 1 and this also 1, and this is a uniform density function. Now you have a slope, a line like this, and this has a slope of z. Okay, so y by x equal to z. So you know the straight line equation, y equal to mx plus c, where m is the slope of the line. That means, let's say for the time being, this constant equal to 0. So you can write y equal to mx, and then y by x equal to m, where m is the slope of the line. Now when I say slope less than or equal to m, that means the area below this line. So this area indicates y by x is less than or equal to z. Okay, so just draw this line, this slope line, okay, that has a slope of z. The ratio is less than this number small z, if and only if we get a pair of x and y that falls inside this triangle. So inside this triangle, x and x and y has a value such that the slope is less than small z. Okay. So we are talking about probability of this particular event. So this area is given by this event. So this indicates area of this triangle shown in the figure. So how do you find the area of this triangle? You just integrate it. Integral of, now you can do the integration, or directly you can write the formula. So either you can go by integration, or use a simple formula instead of writing integration. Let me write simple formula. So this is going to be half times base times height. Okay, so 1 by 2. What is the base? The base is going to be 1. So this width, the base is 1, and I need to find the height of this one. What is the height of that point? Because in this line, let me draw again here. When you draw like this, so I want this point. So this height, what is this height? This height is going to be, see, this point is 1, and that is, so y by x equal to z, that is straight line. When x equal to 1, in the x-axis x equal to 1, then y is equal to z. When x equal to 1 implies y equal to z. Therefore this is going to be z. So the CDF of fz of small z equal to z by 2. So this is the CDF of the function when, what is the condition? When z is less than or equal to 1. That is a condition. Now one can ask, is this answer correct? Is this answer correct? Now if this answer is going to be correct only if the slope happens to be such that we get a picture of this kind. Okay, that means this answer is correct if z is less than or equal to 1. What if the slope is more than 1, greater than 1? In that case this answer is not correct. So we need to consider that case also. Therefore when the slope is less than 1, then this formula is okay. If I consider a different slope, a number little z that happens to be slope of this kind. Suppose let me use another color. Now here the slope is not less than 1. Here slope is y by x is greater than 1. It is not less than 1. Okay. So slope is the z value is greater than 1 in this case. So we need to consider this case separately. So therefore in this case the picture changes, and in that case we get a picture of this kind. Now I need to again find the cumulative distribution function. So this is a line here of slope z again, and this is the intersecting point, and this is a second case, okay, in which our number little z is bigger than 1. So here the z is bigger than 1. Okay, now how do you proceed in this case? Once more the cumulative is the probability that the ratio is less than or equal to that number. So that means your CDF I need to find out. So fz of small z equal to probability of capital Z is less than or equal to small z. What is the small capital Z? Capital Y by capital X less than or equal to small z. Now what is this? This is the area under the line. Which line? This line. Okay. Now what is the area? You can find this area. This is the area. This area. So that area I need to find out. So see, either you can calculate the area which is shown in the red part using this one, or the other way also you can find out. Therefore, this probability P of y over x less than or equal to z, okay, is given by that the area falls below the slope line, okay. And we are going to talk about this event, this event. So to find the probability of this event, we need to find the area of this red shaded area. So how do you do that? So one way of finding this area, red shaded area, is to consider the whole area. What is the whole area? Whole area equal to unity, 1 times 1, it's a square, right? And subtract the area of this triangle. Take this triangle, because finding the area of the triangle is little easy. Just now we did in the previous case, okay. So therefore that event is going to be the total area 1 minus the area of the triangle, area of the triangle. So therefore 1 minus area is 1/2, base is, let's say, let me draw the figure again here, change the color. The line is like this. Now it is intersecting this point. This is z, and this is y, and this one is x, and this is 1. So now y by x equal to z, and what is the y value in this line? In this line y equal to 1. So 1 by x equal to z. Therefore x equal to 1 by z, okay. So therefore this width is your 1 by z, and this width is 1. Therefore 1 times 1 by z. So the CDF is going to be 1 minus 1 by 2z. So this is the CDF of z when the case z is greater than or equal to 1. This condition is very important. So second CDF. So we got 2 CDF now, okay. So we are basically done now. I guess now if you want to have a complete answer, then you should also give the formula for z is less than 0. 3 cases I am considering here. One is z is less than or equal to 1, that you already I did. Z is greater than or equal to 1, that also we did now, this one. And then one more case, let us consider when z less than 0, what happens, because that gives a complete answer. Because see, you have the random variable for only for positive values. For negative values, the random variable is not defined. Therefore, for CDF of negative values, then your fz of z is equal to 0. Okay, since our random variables are positive, there is no way that you can get a negative ratio. So the cumulative distribution is equal to 0 in this case. For negative values, we are not defining the random variable, so there is the ratio also going to be 0. Now let us plot the cumulative distribution function. So I have 3 CDF now. The CDF 1 is fz of z equal to, I can write like this. The first one is where is it? It is here, z by 2. Z by 2 if z is less than or equal to 1. 1 minus 1 by 2z if z is greater than or equal to 1, and 0 when z is less than 1. Okay, so this is my CDF. Now let me plot this CDF and let us see how it looks like. Okay, so we can take it and then we can take its derivative in order to find the density function. So the cumulative that we get starts at 0. See, for say this is z and this is your CDF fz of z, or maybe I'll draw it clearly properly. This space is not sufficient. This is fz of z, and now for z less than 0, your CDF is 0. Therefore, it is 0 in this place. It is 0. Then once it reaches, when this point is, let's say 1, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. Okay, so in this region it is no linearly increasing. It reaches the position of sorry, this is wrong. Maybe 1 2 3 4 let's say 1 2 3 4, yeah. So it is slowly increasing and reaches 1/2 when z equal to 1. When z equal to 1, it reaches 1/2. Okay, and after that this this CDF will take over. So after that it is 1 minus 1 by 2z. It is let's say 1 minus 1 by 2z. Let's put z equal to 2 in this case. If you put z equal to 2, then 1 minus 1 by 4, which is 0.75, right? So when it reaches 2, then it reaches 0.75 like this. So it increases like this. Okay. Slowly it goes like this. This is a CDF. Okay, so here 0, here the CDF is 0, and here this is z by 2, and here it is 1 minus 1 by 2z. So this is the CDF of the function fz of z. Now what is the second step? Our cookbook procedure, take the derivative. Okay, now you are to take the derivative to get the density function. Okay, so now, so in this place 0, if you take 0 derivative, then it's again 0. So it is 0 here in this place. I have shown the yellow color, and then here the slope is constant slope. If you take derivative, you'll get a height of 1/2 like this. After that, this is no, you take the derivative of this. What is the derivative of that one? 1 by 2z square. Okay, so this is kind of function like this. It goes like this. So this is my fz of z, density function of the random variable of interest. Okay, so now we are done. Okay, so you see that problem involving functions of multiple random variable are no harder than problems that deal with a function of a single random variable. In the last lecture and all, I discussed like y equal to g of x, and now I discussed g of x comma y, which is nothing but z. So both are almost same. Okay, multiple random variables are not no harder than that of the single random variables, than that of the function of single random variables. The general procedure is again exactly the same. You first find the cumulative distribution function, and then you differentiate in order to find the density function. The only extra difficulty will be that when you calculate the cumulative, you need to find the probability of an event that involves multiple random variables, and sometimes this could be a little harder to do because it involves no more than one random variable. Okay, now by the way, since we dealt with this example, we will ask a couple of questions. The first question is, what do you think is going to be the expected value of the random variable? What is e of z? What do you think? Okay, what do you think is going to be the expected value of the random variable z? Let's see, the expected value of the random variable z is going to be the integral of small z times the density function fz of z times dz, and integrate from minus infinity to plus infinity e of z. Now your function has three ranges. The first one is from integral of minus infinity to 0. Here the density is 0, you can leave it, z times dz. and now from 1 to 0 to 1 z times the density function is what is the density function? It's a constant, right? It is 1 by 2 times dz plus 1 to infinity z times 1 by 2 z square times dz. Okay, now anyway this is some finite value it gives, and this is going to be 0. And what do you think this is going to be? I'm sorry. So let me change the color. What do you think this is going to be? See, if you look at this one, you are integrating 1 by z all the way to infinity, right? So this is 1 to infinity. Okay, this maybe let me rewrite this one. 0 plus, if you integrate, this is going to be let me write as it is, no problem. Z by 2 times dz plus integral of 1 to integral of 1 over 2z times dz, and the range is from 1 to infinity. Okay, now you are integrating all the way to infinity. Okay, so 1 by z has an integral which is logarithm of z. If you integrate this, you will get a ln of z, right? And the limit is from 1 to infinity. When you substitute infinity, then it goes infinite value. Since a logarithm goes to infinity, this means that this integral is also infinite, right? Therefore the second part is infinite, and the first this one is finite. Therefore finite plus finite value plus infinite value is going to be infinity. See, the expected value of z is going to be infinity. Okay, it is going to be infinity. So the expectation of the random variable z is actually infinite in this example. So there is nothing wrong with this. Okay, lots of random variables have infinite expectations. If the tail of the density, look at here, there is a tail of the density function, tail of the density. If the tail of the density falls kind of slowly, it is going very slowly actually, as 1 over z. Okay, if it is 1 over z square, no problem, it falls very fastly. Okay, falling off will be very high. But if it falls very slowly, okay, as the argument goes to infinity, then it may well turn out that you get an infinite integral. Okay, so that's how things often are, nothing strange about it. Now since we are in the business of calculating expectations, we can ask one more question, like this e of z equal to, see, z equal to y over x, then this is expectation of y over x. Now one can ask a question, would be reason on the average, would it be true that the expected value of z is this number? Can I write like this, e of x by e of y? Could it be true this one is, or could it be that it is equal to this number, like y by x, right? I am writing wrongly. This is y and this is x. Okay, so could I write like this, times e of could it be correct, or can I write like this, none of the above? Our question is, or this is correct, 1 is correct, or 2 is correct, or 3 is correct? Which one is correct? That's what we want to find out. Okay, is equation 1 correct, or is equation 2 correct, or is none of the above correct? None of the above correct. Which one is correct? That let us find out. Okay, the equation number, by looking at this three results, equation 1 is not correct just because there is no reason it should be correct. Why? In general, you cannot reason on the average. Okay, the expected value of function is not the same as the same function of the expected value. Okay, you take a expected value of the function g of x is not the same as the function of the expected value. Okay, there is no reason, okay, why this is correct, why this should be correct. Okay, but this is only true, this one is true. I already mentioned in the one of the previous lecture. If you are dealing with the linear functions of random variable, suppose if you have ax plus by, then this is a linear function. If you have like this, then this is hold up. The expectation of the function is equal to the function of the expected values. Okay, so that is not correct here, because z equal to y by x is not a linear function, it is a non-linear function. Okay, non-linear function of x and y. So this turns out not to be correct. Therefore, 1 is not correct because they are not linear functions, and one cannot say that the expected value of a function is not the same as the same function of the expected value. Now, what about the second one? Second case, we said e of y times e of 1 by x. Is it correct? This one we can ask, is this correct? Well, we assume that x and y are independent by assumption. So therefore 1 by x is independent of y. That means if x and y independent implies that 1 by x is independent of y. Why is this statement true? Independence means that one random variable does not convey any information about the other. So y does not give you any, random variable y does not give you any information about x. Okay, y does not give you any information about y. That is the meaning of independence, independent random variable. Similarly, if this is a condition, if x and y are independent, then y does not give you any information, sorry, this is x, 1 by x. Okay, so therefore the function of one random variable will not provide the information about the other random variable. Or to put it differently, if two random variables are independent, functions of each one of those random variables are also independent. Meaning, let's say x, the function of x is g of x, and you have another random variable y, the function of the random variable y is h of y. If x and y are independent, then g of x and h of y are also independent. Therefore, when you have the expectation of like this, expectation of y over x, then you can write expectation of y times 1 over x. So this is the independent random variable. So when you have independent, then expectation of product of two independent random variable is the same as product of expectation of those two random variables. Therefore, I can say expectation of y times expectation of 1 over x. Okay, these two random variables are independent, and since they are independent, this means that the expected value of their product, so this is the expected value of their product, is equal to the product of the expected value. So this is the product of the expected value, product of the expected value, and this one is expectation of the product. What are the product? Y times 1 by x. So this relation actually is true. Therefore, your E of z equal to expectation of y over x, which is expectation of y times expectation of 1 by x. So this relation holds true. So therefore this is true. So that brings to the end of this problem. Okay, now we have this general procedure of finding the derived distribution by going through the two-step procedure, that is cookbook procedure. The first one is find the cumulative distribution function and then take the derivative in order to find the density function. Now one can ask, are there some cases where we can have a shortcut? Are there some cases where we can shortcut? Okay, it turns out that there is a special case or a special structure in which we can get directly from densities to densities. Okay, like the density of let's say fx x is given, and from x, from the density directly I can get the density of y. Okay, I think my pen charge has gone. Okay, let me continue this lecture in the next class. Okay, so if density of x is given, and then I can directly find out the density of y instead of going through this two-step cookbook procedure. Okay, so directly just by using a formula, and in that case we don't have to go through the cumulative distribution function first, that is finding the cumulative distribution function first and then taking the derivative. Okay, and this case is also very interesting because it gives us some insight about how one density changes to a different density and what affects the shape of those densities. Okay, so the cases where things easy is when the transformation from one random variable to other is a strictly monotonic one. So whenever you want to use the shortcut formula to move from one density function to another density function, provided that the densities should be monotonically increasing function. It should be monotonic. Either it should increase monotonically increasing or monotonically decreasing. That means what? There is a one-to-one relationship between x and y. So whenever you have one-to-one relationship between x and y, then you can use this shortcut procedure. Okay, using the shortcut procedure, you can directly get the density function of y from the given density function of the random variable x. Okay, so there is a very straightforward procedure that I will discuss in the next lecture, upcoming lecture. Thank you very much. With this, I will stop it now.